Yeah, that's my daughter's. What about comparing means? Which one of these examples is the easy one? Who's going to take the low-hanging fruit? A. We stand with you. It's A. So you see, like, what my point was when I asked you for takeaways, that like that first takeaway that we had on that first slide tells you how to compare those things and say distinguish them, because a lot of it starts to mix up. That's what worries me about the T. By the time we get to the T, we'll have so much material, and so these are the kind of things that'll help you navigate that. I think this is Dennis's. What do you think, Dennis?
I'm sorry, the second one, sorry. I'm going to go with A. Not really sure.
What do you think? You stand with Dennis?
Yeah, always smart guy.
I think he did get one of the highest scores on the WPR, actually. So,
What'd you get?
I don't remember.
Is A correct?
His A is correct. Why is B not correct? What are you trying to... So I think I answered this one. It's A. It's A because what you're trying to do when you simulate a null distribution, you're trying to assign things as if they were random chance. That's the null distribution. That's the null hypothesis, right? That there was no effect, and all you're seeing is the noise of random chance. And for that to happen, it means that when you have yawners and non-yawners, and they're randomly assigned to yawn seed and non-yawn seed, you're going to get, you want to see what that looks like. And you repeat that over and over because you want to get that noise. There's some noise for randomness. The one I like to give you is if I step on the scale every day, I'm not exactly the same weight every day. There's a little bit of noise, around 122 pounds. And, you know, when they ask me at the doctor's office, what's your weight, I give them the 95% confidence interval. And then my treatment stops. There's noise, right? We don't think we're going to treat you here. You better find another doctor. But the reason is because when it's not ever, you can give them the mean weight, your sample average weight, but it's fluctuating inside this kind of interval, and that gives you the noise that's involved in randomness. The same thing here, you're trying to pick up not just sample, but the noise that you would get if they were randomly assigned. So that's a good takeaway. That's a good takeaway for simulation. That what you're trying to recreate with simulation is the noise. So what's the difference when we compare means? The process. I'm just going to go through the process. It's not my typical way, but I just want to get through this so we can do some R coding. So the example that I started going over with you is that there were two groups. There were sleep-deprived people and unrestricted folks. And I'm comparing the average change in their reaction test scores in both groups. And my null hypothesis is what? There's no difference between the two groups. They're going to end up with the same test scores. And what's the alternative hypothesis then? There is a difference. So now I have those two lined up. How do I simulate the null distribution for this example? So I'm just highlighting what's different. Because you had 2 or 3 sections about proportions, and then you have 2 or 3 sections about means. So I'm smoking through those sections right now. So by leveraging what we already have for proportions. Can I use the same method I did before with the yawners and non-yawners? No. Why won't that work?
There's different amounts.
Yeah, it's different. You're not looking at groups of how they fall out. You have an average. That's a number. You can't just assign a number, a quantitative number to 2 groups. And so that's not going to work. My null distribution's got to exhibit no difference between the 2 groups beyond random chance. That's what it's got to do.
Could you use the mean and standard deviation to create your own,
You're heading towards a theoretical one, so I'm going to get to that. And I saw from your homework you didn't like the theoretical one. So I'm going to go through that a little bit more slowly so you can crank through that. Because that's an easy question to ask. Crank through a z-test and give me the 95% confidence interval. But we'll get there. So how would I do simulation is that you're generating with a computer what that null distribution may look like. And so the way we do it, the first step is You count out no cards. Not last time I had playing cards, and some were red and some were blue, and the red was supposed to represent yawners, and the blue was supposed to represent non-yawners. Remember that? Here I can't do that because I have what we call a continuous variable, continuous. So in each card, you're going to write down one of those 21 improvement scores. There were 21 subjects. They all got an improvement score. You're going to write it down on the index card. So that's the first step. You're going to count out your subjects as index cards, and on each index card is going to be an improvement score. That's what's different. For the proportions, which I probably misspelled, I just needed 2 colors, yawners and not yawners. Here I have 21 different colors, each one representing the improvement score. That's the big takeaway that's different. Then I shuffle the cards, and I stack it into 2 groups. The sleep-deprived were 11 cards, and the unrestricted were 10 cards. So I just put 11 of them into one stack, and 10 of them into the next stack. You should take notes, actually. The literature says that if you take notes, you learn better. Just telling you, that's what the science says. And it also slows me down, because now that I'm getting more sleep. So little people like me that like to play basketball, our only hope is to run. So I can go fast. Premise is that the scores randomly fell between the 2 groups. That's what the idea is behind it. Then you calculate the average in stack 1 and the average in stack 2. And so you get these averages. That's 1 repetition. I think you have these weird questions sometimes. What's 1 repetition? So this is how you get the 1 repetition. And then you do it how many times? 1,000. They make you can do it 1,000,000. You got a computer, you can do that. Government issued computer. So you just keep going. And then you calculate this difference in means, because you always work with the difference. So the null hypothesis would be that this difference was 0. And what should the average of all of these guys be if you did it 1,000 times? 0, because it's due to random chance alone. So if you took the average of this column, you're going to get 0 at the end. And in your simulation, you'll see a plump right at 0. Does this make sense so far? So when Colonel Kaminsky told me that the way to teach things is using simulations, I told him it's kind of looked at me like, how are you going to do that? Because I was kind of like Ryan was thinking. I would just take my theoretical curve, calculate the standard deviation, and do that. I was kind of headed in that direction. But this is actually easier. It makes sense. So this is my version of a bell curve. I was tired. So you see that the way it should look when you run the simulations is that you will get a bump right at 0, and everything will, you're less likely to get these differences out here. You're more likely to get this difference out here. So the difference in means for 1,000 reps would look something like that. And then to keep going, the difference in means we found from our sample is 15.92, and you count how much is in here. So you just counted up what percent ended up in here, and it turns out that's the p-value. So it's the same old, same old. Once we got to this point, it's the same old, same old. So you can understand why 206 is taught the way it is. You have a theoretical formula for that curve, and you just crank out these p-values every time, just area under the curve. It's just harder to understand what's going on. They have their applets. I'm not teaching you anything more about the applets. It's a waste of our time. But this is what it looks like. They have the stack of the treatments. I think A was sleep deprived and B was unrestricted. They have the means, and then they have, this is the simulation if you did that thing with the index card and used a computer to do the index cards. That's what it turns out like. And then right over here is the greater than 15.92. That would be the p-value, that red chunk. And that's 6. There were 6 people that were in that red chunk divided by, I guess I ran it for 1,002. I have no idea why I did that. So what do you think? Is there evidence for rejecting the null?
Yes.
Why?
P-value is greater than
Yeah, the p-value is less than 0.05. Right. So there is evidence for rejecting the null.